Okay, so perhaps I'll introduce the next speaker before they set up. So the next talk is on Smeariness, Begets finite sample Smeariness, continuing with the same theme. And the speaker is Tran from the University of Göttingen.
Okay, so thank you everyone for being here. I'm glad that my talk it's just after Benjamin's talks. So we're in the same theme. So what the purpose of this one is that we will look at Smeariness in, I suppose, in a different or in a wider context, where we'll look at more general manifolds, for example, symmetric spaces, and then we not only look at Smeariness when we have the Hessian of the Fréchet function vanishes. And one thing we find out is that it can also happen if we have a zero eigenvalues of the Hessian of the Fréchet functions. So then we'll have Smeariness in terms of some direction only. So we don't just spread out in all directions, but we spread out in some direction. In some other direction, we don't spread out. And it will affect the testing and the theory of Smeariness, and we'll see in this talk. So the outline would be I will introduce some notations and recall some theory, some definitions from Benjamin's talk, and then we'll discuss about Smeariness and finite sample Smeariness and their relations. And we discuss about, well, a different kind of Smeariness, and then I show a small simulation test. So here's the notation. In our setup, we have M to be a complete Riemannian manifold with a geodesic distance. So we can think of, well, spheres or shape space, Grassmannians, or more generally, if we would want to think of, it would be globally symmetric spaces. And then we have random variables that are IID with an underlying probability P. And then we have a Fréchet function and we have sample Fréchet function as usual. So normally when we do Fréchet analysis, we will have some typical assumptions. First is that, well, we are not that our random variable is not a single point. And our Fréchet function is finite. We have a unique Fréchet mean. Our cut locus has measure zeros, or we can turn it into a more geometric condition is that the cut locus of Fréchet mean is either void, that means we don't have a cut locus at all, or it can be reached by two different geodesics. So the upshot is that the probability of the cut locus is 0. Based on the result done a really long time ago. And then the assumption 5 is that we can write the Taylor expansion of the Fréchet function when we will look at the Fréchet function composed with the exponential map in a local chart at the Fréchet mean. And then we can actually say that we can diagonalize the Taylor expansion in higher degree. This one is more about simplicity when we deal with analysis of the Taylor expansion of the Fréchet function. So being diagonalizable is not a trivial assumption, but it's something that I think we're willing to trade. Especially when we just look at the second order of the Taylor expansion, then it's always diagonalizable. So we have some notation. We have, I just recalled the notation from earlier talk from Benjamin. We have the Fréchet empirical Fréchet mean. We have the population variance, the Fréchet sample variance, and the modulation. And then here we'll look at the definition of smeary and finite sample Smeariness. So, well, the random variable is Euclidean when modulation is 1. And we have finite sample smeary when the supremum of the modulation is greater than 1 and smaller than infinity, as Benjamin pointed out. I don't look at the type 1 and type 2, just call them finite sample smeary. It is smeary when the supremum of the modulation goes to infinity. So that's the important point. So we always see that it's smeary when the Taylor expansion of the Fréchet function has the second order vanish, right? So, well, then it turns out that we call that R power smeary, and when R is 0, that means it's just 0 power smeary, or the second order of the Fréchet function at the Fréchet mean vanish. So then we have some relation. If it is R power smeary, then it is smeary and it's implied finite sample smeary. And well, so the corollary is that if the Hessian of the Fréchet function, or the small f here is the Fréchet function composed with the exponential map at the Fréchet population mean, if the Hessian vanish, then we have smeariness, right? Well, but then if we look at that, well, if the Hessian doesn't vanish, but it's kind of singular, right? The rank is not full rank. So that means if we have an eigenvector that has eigenvalue 0, then we also have smeariness. That means when we do the testing, we do see finite sample smeariness, and we cannot, like, that mean in the sample central limit theorem, we do have to lower the rate, or to n to power 1/4, for example. So then we call that terminology directional smeary, and it also implies finite sample smeary. So in this talk, well, I deal with kind of two conjectures. So the first one is that if we have a random variable that is smeary, and then, well, the question is, well, is that true that, well, if we look around that measure, or look around that random variable, do we often find a measure that is finite sample smeary? And also the question B is that, is smeariness kind of singular in the sense that it's actually a set of measure 0, but then if we look at directional smeary, right, we don't require the whole Hessian to vanish, we just require it to be singular, then it turns out that, well, is it not as singular as we think, right? So that's the question that I want to address here. So for the first question, suppose we have a random variable that is R power smeary, and then we look around, right? So then we'll see that, well, we can find a random variable that is finite sample smeary, that is arbitrarily close to our smeary sample, random variable. And intuitively, it is right? And so to prove this, well, we kind of look at the convex combination, or we think of kind of convex geodesic, right? Connecting our smeary random variable, and we'll, for any geodesic pointing out, we'll see that there will be a finite sample smeary random variable along that geodesic, and that's the proof. And then the corollary will be that if we start with a directional smeary random variable, then we will also find a finite sample smeary random variable close by that the random variable that we start with. So that's the first question, and it is affirmative. So the second question is that, well, how about directional smeary? Is that really singular, and is that easy to see or easy to find, right? So if we think of a smeary as a kind of a single point, directional smeary is a singular facet. So then well, so that gives us some idea about the structures of the probability measures, where we have smeary distributions at the corner, and we have directional smeary as some facet. So then, and nearby we have finite sample smeary distributions, right? And it's not hard to find. So in this case, we don't solve the question or answer the question for any compact Riemannian manifold yet. So we actually only answer for some certain Riemannian manifold. And an example is can be thought of as spheres, Grassmannians, or more general as global symmetric space of compact type. So here's a theorem. If we start at M, as some of the example in just list out, or in general it is a Riemannian manifold of sectional curvature bound above by K, and then we actually have a copy of a connected geodesic submanifold. Geodesic submanifold of constant sectional curvature K inside of M. That means it's technically we have a copy of the sphere inside of M, and that is a theme for globalistic metric spaces of compact type. And if that is the case, then we can find a random variable that is directional smeary. And actually, we can prove more in the sense that if we start with arbitrarily measure, then we can find a close by measure that is directional smeary. But it's not in the paper. It's what we're doing in the next one. But in here, we can see the kind of the technique or the kind of the theme. And there's an interesting thing that I want to point out here is that if we look at the measure, so first, in the proof, we have N to be simply connected to the geodesic submanifold of constant sectional curvature, or it's a sphere of curvature K. And then we have a point at N. And we look at the two orthogonal unit vectors that are along that are tangent to N. Then now we think of we want to construct a measure that is directional smeary. Now the measure that I'm going to construct is singular. It's just along a geodesic, along a grid circle, but it is directional smeary along the other direction, the orthogonal direction. So if we think about it, we have a geodesic gamma T. It's a tangent to direction V, and then there's direction W that is orthogonal to it. And then we have 3 points along V, which is first mu, it's a middle point, and 2 further point away. And our measure is just supported at that 3 points. And then that measure is directional smeary along W. That means if we take samples and we compute sample means, then the sample will spread along W, not along V, by the rate of the fourth root of n, and that's an interesting point, and that proved the theorem that we can construct a directional smeary measures on the manifold M. Okay, so here's a simulation. When we look at the shape space, which is a kind of example of our space M in the theorem. And in our example, we look at buckles of microtubules that we eventually encoded as configurations of 5 landmarks. So they are a planar shape space of 5 landmarks. And then we simulate, like artificially simulate the 2 groups so that the means are sufficiently further from each other. Yeah. And then we do the test for the 2 groups in the planar shape space. And then we find out that, both the quantile and the bootstrap test doesn't really reach the power that we want. Of course, here the sample is only 20 points, 20 shapes. But the quantile perform significantly worse than the bootstrap, both in terms of the level and in terms of the power. And so we conclude that, if we in the space where in higher dimension and when the curvature is it's quite high. So in this case, the curvature runs from 1 to 4, right? As we know in the planar shape space. And then the sample size is small, then the 2 sample test is, at least for the quantile 2 sample test, is not reliable. And that's my talk. And thank you for your attention. And
well, thank you very much. So far, no questions in the chat. I think we'll move on to the room just because we're running short on time.
Okay, any question in the room? So maybe just one short question because, I'm sorry for the number of questions, but we're really running out of time. So one question is, so the smeariness and finite sample smeariness is completely linked to the fact that the curvature is positive, or the fact that there is a cut locus. So if we put the cut locus apart, then we have the modulation, which is above 1 if we have positive curvature. But if we take the product, a manifold, which would be the product of positive and negative curvature, then we can engineer the weights between the two manifold so that the modulation would be 0.
So
One, sorry.
Will be
Yes.
1.
So is that entering into your vision?
That's an interesting point. But what I think is that the modulation is affected by the eigenvalues of the Fréchet function. So I guess we point out here, like even when we have a singular measure that is just on a grid circle, then we would think that the modulation would be 1 because it's just a line, right? But somehow the Fréchet mean the sample Fréchet mean just want to leave that direction. So if we have a negative and a positive, maybe the Fréchet mean just want to leave to the positive sides. That's what I'm thinking.
So what you think is if it's really smeary, then it's gaining against the negative curvature, which would be the acceleration of the convergence.
Yeah. Okay. Or in some direction, it just want to stick to the population, but in some direction, it just want to leave, and we forced to expand the or to multiply by the direction that we want to leave, right? Because we want to rescale so that that direction is not blow up. That's what my thinking is. Of course.
Okay. Good. Thank you. And then we are move on to the last talk by Quentin. So
Oh,